Okay, hello everyone. So welcome back. So now we goes into the second session of our tapas. I think let's wait for Hajo. And our next speaker is Venice. Actually, she passed me the video, the pre-recorded one. So I think Hajo got the broadcast through at his side, and then I think Manny is gonna do um, just for the QA session. So the pre-recorded talk will be broadcast and live stream on YouTube. Let's wait for Hajo, and we will start in 5 minutes. Venice, can you test your microphone? Just make sure you can speak. We can hear
Yes. Can you hear me okay?
you. Yes, good.
Great. And thanks, Yulai, for sharing the video.
Yeah, we'll do that. I think Hajun probably has a microphone problem, so I will broadcast at my side and then followed by the QA. We will start in a few minutes. Can you guys see my screen?
Yes.
Okay, so okay, so let's start our first talk. So given by Menis, the title is API Analytics for Querying Static Analysis Rules. Let's start.
principal scientist at Grammatic. Today I'll be talking about our work on using API analytics for curating static analysis rules. This is work done with lots of collaborators at Grammatic, and this work was funded by DARPA. Using third-party libraries through their API functions has become a very common software development paradigm. Most modern software across different programming languages heavily make use of third-party libraries. According to libraries.io, there are over 5 million open source library packages available across multiple different package managers. In fact, it's now very easy to find libraries in your favorite programming language. C++ has Conan, JavaScript has NPM, Python has PyPy, and the use of libraries in software development continues to skyrocket. However, developer tools like static analysis have not really kept up with this rapid increase in library API function usage. As we have seen, there are numerous API functions and they can be complex to use correctly. And they can often have incomplete and insufficient documentation. And the incorrect usage can cause security, reliability, and performance issues. Static analysis tools, for the most part, are missing a large chunk of these kinds of bugs. Now, it's true that static analysis tools can already find incorrect usage of API functions. However, a static analysis tool can only check for the violations of the rules that it is providing. So, for example, tell it that you shouldn't double free a pointer or dereference an already freed pointer, or when read or write past a buffer's boundaries. Now, given a programming language, after checking for all the generic language level bugs like buffer overflow and null pointer dereference for C and C++, it can be a long uphill battle to be able to check for the correct usage of thousands of API functions and sort of finally come up with rules for all of these. And in many cases, even though a bug that violates an API function's preconditions, ultimately it might manifest as a generic language level bug, but we may want to report a warning to the programmer at the API function level, as the fix is more likely at the API function boundary. That is, adhering to the API function's preconditions and not really a change the implementation of the API function itself. Now, one way to scale to a large number of API functions, which is the methodology that we use, is to use the wisdom in big code. That is, learn from how most developers use API functions. Now, automatic specification mining has been of interest in this community for a while, but such techniques typically suffer from very high false positive rate, because even if a single mined specification is incorrect or uninteresting, it can cause a large number of reported violations, which are all viewed as basically false positive. And therefore, we propose a semi-automatic workflow for curating static analysis rules. And then I'll talk about a couple of case studies based on this work. So we start with a large code corpus, and acquiring this has become much more easier than in the past, especially in the past few years. We then run static analysis tools on the code. Typically, analysis tools create detailed intermediate representations of code and provide the infrastructure to capture different semantic properties of API function usage. We collect properties about API usage based on these intermediate representations and put them in a database. A static analysis developer can then interactively issue queries to this database and understand the API usage behavior in terms of the extracted semantic properties as an aggregate for the entire corpus. And they can review the results and fine-tune the queries and kind of repeat this process. This can be viewed as a data analytics process, but instead we're applying this on rich semantic properties extracted from API usage on a large code file. The developer would then curate the rules based on the insights from this interactive process, which will yield potential rules, but will triage the rules to actually create the final set of rules. And we would write checkers based on these rules. Ideally, we would reuse a lot of the existing static analysis infrastructure and enhance the static analyses with the ability to find violations of all of these. So with this kind of general setup, I would like to talk about a couple of case studies in two programming languages where we applied such a methodology. First, for C and C++, we took the Fedora source RPM package corpus, which is over 400 million lines of C and C++ code. We then run a static analysis tool called CodeSonar on all of this code. CodeSonar is a commercial static analysis tool primarily geared towards deep analysis of C and C++ applications. We then tap into the rich semantic representations of programs that CodeSonar produces and collect a variety of information about API function usage. For example, is the return value of an API function used? Is the argument provided to the API positive or zero? And if the argument provided to the API is a pointer, then is the memory that it points to initialized, and so on and so forth. Then we interactively issued and refined queries in order to find potential static analysis rules. For example, we find all the API functions that are used in at least some number of projects, so that there's enough diversity in the API usage. And also they have the API function is called at least some minimum number of times, so that there's enough data to support and validate our rules. And as an example, the return value for the particular API function was used in at least Y% of the call sites. And typically this is pretty high, 95% or 98% of the times the return value was used. And overall, there were no more than some number of violations in the corpus. This is because if you had a million function calls and in 98% of the cases, the return value is used, and in 2% of the cases it was not, it still means there would be about 20,000 violations if we make up a rule that says you should use the return value of this particular API. So this is kind of an interactive process where we try to come up with reasonable parameters that yield interesting looking rules. And then finally, we look at the actual potential rules and kind of eliminate the silly or the incorrect rules through a process of triage. Now, spending some time to make sure that these rules are reasonable is worthwhile, because otherwise a user who's using the static analysis rule based on these rules might have to spend a lot more time getting frustrated with lots of false positives. And so these curated rules in this particular case are of the form the return value of a particular API function should be used. So as a specific example, the return value of gstir escape library API should be used, and then the static analysis is taught to find violations of those rules using pretty much like an existing infrastructure to find lot more bugs. So in this particular case, we were able to produce such return value check rules for over 1,500 API functions, which is now in production in CodeSonar, and a subset of these are also part of the Clang tidy open source checker. And we found hundreds of bugs in the real world code based on these API function checkers. As an example of some of these bugs, we'll take the glib API function, or the API library. And the glib API library is a grab bag of various genome utility libraries with over 1,600 functions and about 80 string utility functions, and manual editing specifications for all 1,600 of these. They're very daunting task. And moreover, the correct API usage can actually be quite subtle. So, for example, the ASCII up function converts an input string to an uppercase, but it does this all in place, whereas the string escape function escapes certain characters in the input string to make it safe. But the safe string is actually allocated in a new string when returned, but it leaves the input string completely unmodified. So you need to be very careful depending on the specific string API, whether the input string is modified or a new string is allocated and returned. And so using our workflow, we were able to identify, as I mentioned, the return value of G-star escape is used in an overwhelming majority of the cases, and therefore we created a rule saying the return value of escape should be used. Actually, for many violations in real code, and a number of them turned out to be fairly important problems. So here's one such violation that we found in the real world Linux package. So in this particular case, the param string comes from the user and therefore can be unsafe to use in an SQL query. Therefore, the developer uses the G-star escape API in order to escape some of the characters in this user string. But note that they actually don't use the return value, they drop this. So this has the problem that the newly allocated escape string is a memory leak, but more importantly, the developer has kind of assumed that the input string has been escaped and made safe, whereas according to the specs of G-star escape, it actually leaves the input string completely unmodified. The param string is then later used in constructing this SQL query, and therefore this is kind of a typical SQL injection attack. And so this was specifically one semantic property, the return value usage, from which we were able to create lots of API rules. Here are some other examples of semantic properties that we extracted. So for example, is an argument to an API function at a specific position, non-negative, non-zero, it's a pointer. When you dereference that particular pointer, is it initialized? And if you dereference that particular pointer, is it initialized to a non-empty string, and so on. And here's some example rules that we can find from data collected over a large corpus on lots of APIs based on these properties. So we're able to infer, as an example, that the third argument to the memset function, which is the length of the buffer that you're trying to set the memory for, that should be non-negative. The first argument to strcat should be non-zero or non-null, otherwise it's undefined behavior. Similarly, the first argument to pthread mutex unlock is a pointer, which when dereferenced should be initialized. In fact, it should be initialized with the pthread mutex object. And the third argument to XML new child from libxml2. So that should be a pointer, which when dereferenced should be initialized to a non-empty string. So this third argument turns out to be the name tag of the new XML child that you're creating, and an XML tag should have a non-empty string name. Otherwise, it's incorrect behavior. So we're able to kind of derive all of these rules by applying fairly simple statistical kind of checks on data, QData, based on extracting these properties. So switching gears a little bit, let me also talk about a similar workflow that we applied to JavaScript. So we looked at the Node Package Manager corpus, which has over 700 million lines of JavaScript code. And we used the TypeScript compiler as a lightweight static analysis engine. And we ran this on all of the corpus. So the TypeScript compiler performs mostly local data flow analysis for its type inference. And as a result, it produces various semantic program representations. Using these, we extract various program properties. For example, is an argument passed to an API at a given position a fixed string? That is, can be statically determined using local data flow analyses that an argument is a known fixed string. Then we can issue queries interactively, similar to before, sort of focusing on this APIs where an argument is not a fixed string in an overwhelming majority of. And we're basically trying to find out if there are APIs with arguments to which you should not be passing hard-coded strings, which are typically secret values. Then in a similar manner, we look at all the potential rules, eliminate some of the silly or potentially incorrect rules, and create rules of this form. Like the second argument, the JSON web token sign function, which is the passcode, should not be a fixed string. And then we can feed such rules to a modified version of TypeScript and find bugs. Here's some example violations that we found in NPM packages. So the JSON web token sign function had hard-coded passcodes passed to it. The verify function had a hard-coded password passed to it. Encrypt functions had hard-coded passwords passed to it, or hard-coded keys passed to it. And surprisingly, we found like database connection APIs used a lot of hard-coded passwords. We found over 100 instances of such violations for some database connection APIs. So getting to some insights from all of these case studies. One, the performing interactive data analysis and particularly triaging any of the potential rules that came up through this analysis was very important for quality control, also explainability. And instead of starting from scratch, using existing static analysis infrastructure was very helpful in a couple of different places. So one, by running static analysis on lots of code, we can tap into rich semantic properties that these analyses can extract about API usage rather than just surface syntax. And also we can make existing tools much better by reducing their false negative rate. So for example, CodeSonar and ClankTidy already had most of the mechanisms for return value checking for an API. We just provided them further with a large list of APIs to do that for increasing the utility of this feature. So with that, I'm open for any questions. Thank you.
Okay, thank you, Venice. So any questions from the audience? So Venice, I have a question regarding the, so because the frameworks seems to me is semi-automatic, right?
Yep.
So I was wondering because while doing static analysis, lots of dark code, which basically does not have implementation available or source code available. So we need to sort of handwritten summaries for those APIs. So whether I'm not quite sure whether your framework could be somehow useful to automatically generate some summaries. For example, whether it might have side effects for particular pointers when passed in the API function call. Would that be somehow you have been, your team or
Yeah,
Tech working on to automatically generate
absolutely. So I think I probably don't have the statistics at the top of my mind, but many of these library functions actually end up being part of other packages because we were looking at the Linux library package. And so in those cases, yes, you're right that in a good chunk of those cases, you might have access to the source code, just not as part of this project, but some other project.
Yes.
The way we actually end up kind of checking for these rules is by creating summaries. That's kind of an implementation detail where you kind of create a corresponding summary for the kinds of things you are interested in. Like if you're interested in taint analysis, or if you're interested in null pointer dereference analysis, then you're creating summaries corresponding to that specific view. Because in general, like summaries are only partial specifications typically, and they can depend upon the specific analyses. So in the end, the way these rules are integrated is by kind of automatically emitting summaries. I guess the main point was that eh, eh, while we initially started out wanting to make this kind of fully automatic, it turned out that spending a little bit of developer time to curate the rules, because again, we are trying to guess these specifications from lots of code, right? Because it's not like written up somewhere. You're trying to infer this behavior based on how most developers use the particular APIs, and therefore spending a little bit of time in looking over the quality of the rules ends up helping quite a bit in the final sort of product that you create, rather than trying to make this a fully automatic process, which is what we had originally started out with.
Okay. Yeah, I think quite interesting because I was wondering, because you mentioned the somehow, because some APIs, they have a specification that could be very tricky, as you mentioned. I think the API for the string, I think for the
Yep.
yeah. So like the lowercase become uppercase also. So in that case, because you're trying to basically, if you automatically want to learn the side effects or the summarization from the specification, I believe this is quite challenging, right? You always have to use some existing static analysis, as you mentioned, the code sona, to like sort of infer at the data flow level the usage pattern. So would that be, if I understand, is that the way you are doing?
Right. So in particular, note that we're only inferring partial specifications, not full specifications of exactly what the function is doing. So if you take into the view of just this partial specification, that whether or not the return value from an API should be used. So in that case, we're using an existing static analysis to track whether across each path, the return value of a particular API was used. And then we kind of look at how that behavior is tracked across a large corpus. And in this particular case, it turns out that if you have the G string ASCII up function where the return value is unimportant, in that case, like pretty much nobody uses the return value, whereas in the case of G star escape, an overwhelming majority of the cases people used the return value, so we were able to flag the cases where they did not use as the bug. So these are definitely partial specifications, and I think what I have sort of listed, the few different things are I think just a initial starting point, I think this is a very rich space where you can essentially mine more and more interesting specifications. But the main thing to be careful about is not introduce a lot of false positives at the rule level, because if you do so, then any violation that you find of those bad rules, if you will all lead to actual false positives, and that can lead to frustration in the users because they'll basically ignoring any violation of such rules.
Okay, so yeah, quite interesting. I think it's mainly aims for bug detection or try to find some bad programming practices by mining your property, right?
Yeah. So again, like all these violations that we found were kind of bad programming practices. In fact, there was one particular project in which every use of the API was incorrect. So you couldn't have found these kinds of bugs based on looking at just a single project and whether APIs are used inconsistently within that. Yeah.
Okay. Yeah. Okay. Thank you. So, yeah. Any more questions? Okay. So let's move to the second speaker. So with our second paper is on verification of commutativity. So may I know who is the second speaker?
Hi.
Please raise your hand. Hello.
Hiya.
Hello, Kappa.
Aditi Kabra. Yes.
Yeah. Okay. So can you share your screen now?
Yeah.
Okay. So feel free to start.
Right. Hi, everyone. I'm Aditi. I'm a PhD student at Carnegie Mellon University. In our work, we developed an algorithm to efficiently verify whether a transformation graph commutes. Suppose that you're working in a units of measure language. These usually allow you to define new units by specifying their conversion from an existing unit. You write this snippet of code. So over here, suppose meters already existed and you're defining the new unit feet by saying that 1 meter is 3.28 feet. You can represent this transformation as a transformation graph, like so, with the units or the types as nodes and the transformation as edges. Now you add a definition for miles, and then you create this new unit wugs that you say is 10 to the 4 wugs is a mile, but also 10 feet is a mile, is a wug, I'm sorry. And then suppose you want to cast a variable defined in meters to something in wugs, and the language allows you to do implicit conversion. There are two possible paths for the compiler to take. If it were to go through feet, you would end up with 32.8 wugs. But if you went through miles, you would have 6.21 wugs. If you want the compiler to be deterministic, you need to make sure that the transformations between the same two units are equal regardless of the path chosen. Commutativity is the property where the transformation from a given source node to a given sink node is the same regardless of path chosen. So to see that the compiler is deterministic, we basically want to check if the transformation graph commutes. Further, we want to do so in an online fashion over the course of addition of edges and raise an error as soon as a bad transformation is introduced. The naive way to go about this is to check if all pairs of paths in the graph are equal. Look at this example where n is the new edge. Throughout the presentation, I will use the dashed arrow to represent the new edge that's being added to the graph. You can see that over here, there are many pairs of paths that will need to be checked to see if checked to be equal to each other if we want to check that the entire graph commutes. Further, in a graph with cycles, the set of all paths is infinite. So the approach of just choosing all pairs of paths is just not possible. And even in an acyclic graph, the set of all paths can be exponential in the worst case, which is far too inefficient. There are also some other requirements that we would like our algorithm to fulfill. Actually checking whether functions are equal can be expensive. So we want to have to check only the smallest number of pairs to be equal. So, and then also we want to verify in an online fashion and avoid repeating the effort of checking pairs that we have already checked. So that was the motivation. Let me state the problem formally. I'm going to be using the term parallel pair of paths to mean paths that share the same source and the same sync node. Here, the green, the blue, and the red path are all parallel to each other. And then I'll be using the term parallel pair, which is just a pair of parallel paths. For example, the green and the blue paths form a parallel pair. And notice that a graph commutes if and only if the paths in every parallel pair are equal to each other. If this graph is to commute, for example, the green and the blue path will need to be equal, then the green and the red path will need to be equal, and the blue and the red path will need to be equal, and so must all the other pairs. The problem I described in the first slide was the online addition problem. But I'm going to reduce it to this verification set problem that given a graph and a new edge returns a set of pairs of paths that need to be equal to each other in order for the graph to commute. Online verification set problem produces these path pairs, and then you can use function composition oracle and to extract the transformation that each path represents, and then a function equality oracle to check if each of these transformations are equal. If all the pairs of transformations are equal, then the output of the original addition problem is that the graph commutes. In this work, we abstracted out function equality and function composition and solved the verification set problem. The reason we did this is that function composition and equality is often domain specific and often hard. For example, in a graphics programming language, functions might be matrices and function composition would be matrix multiplication. So that was the problem statement. Now we go about designing a good algorithm. The first observation that would help us do better than the naive baseline is that we don't care about paths that existed in the old graph and don't involve the new edge. Here, the red pair already existed before adding the new edge st. And since the original graph already commutes, we know that the pair must be equal, so we don't need to check it. However, this green pair did not exist before the addition of the new edge, so we do need to verify that the paths in the pair are equal. The way to identify only all such pairs where one path goes through the new edge and the other doesn't would be a good baseline to start with. So every such pair is going to have a structure something like this one. Over here, the squiggly lines represent paths as opposed to just edges. There is a common source of both the paths, F1, and a common sink, F2. One of the paths in the pair, the one that doesn't pass through the new edge, is F2. The other is F1, the new edge, and then F3. We want a way to identify all such structures in the graph. We know that they pass through the new edge, and we can kind of see that the squiggly lines form a sort of path from the new edge source to the new edge sink, a path where the direction flips twice, once at common source F1 and once at the common source sink F2. We'll call this structure a two-flip tolerant path. We can now alter an ordinary all-path search algorithm to look for two-flip tolerant paths. In the all-path search algorithm, use both backwards and forward edges, but keep track of how many flip points you've used and only allow 2 flips. We now use this two-flip tolerant path search, which is much faster than the naive baseline, but it is still unacceptably slow and returns far too large a set of paths to verify. So to further make improvements, we need a new observation. From the output of the previous algorithm, notice that amongst a set of parallel pairs between the same 2 nodes, only one pair needs to be verified. Because the original graph commutes, we already know that the paths in any other pair are equal to the paths in the pair we've already verified. For example, Suppose that two parallel pairs are the green and the blue pair over here in this diagram, and then the green and the red pair. Suppose we already verify the green and blue pair. We already know that blue and red are equal from the original graph. So green must be equal to red because green is equal to blue and blue is equal to red. Essentially, we can divide the output of the previous algorithm into equivalence classes of pairs, where a pair belongs to the same equivalence class if they have the same source and sink node, which is to say they're parallel to each other. We only need to verify one representative of each equivalence class to check the entire graph. And this observation allows us to write a new algorithm that first makes a choice of source and sink, and then finds a representative pair for this choice. The number of paths is asymptotically tight, but it is not minimal yet. So to reduce the output of this algorithm to a minimal set of pairs, we need to make a final observation. The output of the previous algorithm was a representative for every equivalence class defined by the source and the sink of the paths. But sometimes verifying for one source sink pair implies that the parallel paths for another source sink pair of nodes must also be equal. For example, consider this green pair of the Q1 to Q2 equivalence class. If we verify it, we get this equality, F2 and H2 is equal to G2. Now, consider this other blue pair of the P1 to P2 class. Notice that to verify this pair, we can take the equality from the green verification, pre-apply function L on both sides, and then append function M on both sides. So verifying a pair from Q1 to Q2 automatically verifies all pairs from P1 to P2 also. The general rule is Q1 to Q2 verifies P1 to P2 if and only if there is a path from P1 to Q1 and a path from Q2 to P2. We can use this rule to place the transitive relation for verification on the parallel pair equivalence class, where the relation A verifies B is placed when verifying A implies that B must also commute. Then, with this ordering in place, we need to choose the smallest set of source sink pairs such that their verification implies the verification of the entire graph. You can visualize this process like so. Given this example graph, you can make a graph where the nodes are the source sink pairs, and an edge A, B indicates that A verifies B, where verifies was the transitive relation from the previous slide. You just need to find the roots of this graph, the set of nodes that have no predecessors. Ultimately, you want to return one parallel pair representative for each source sink pair in the set of nodes of roots. In practice, we have found that this optimization results in the fastest execution. To show how our algorithm performed in practice, we tested it on randomly generated graphs of varying size and complexity. So we randomly generated the graphs setting the node count and edge density, where edge density is the ratio of the number of edges in the graph to the total possible number of edges that you'd see in a totally connected graph. And then we measured execution time. In these graphs, the y-axis is time in seconds, and the x-axis is the number of nodes. The color indicates density, and so you can see over here, going from the naive baseline with observation 1 to the 2-flip tolerant baseline, brought down the execution time for 7 nodes and 0.9 density graph from 50 seconds to about a second. Going from the 2-flip tolerant path search to the base polynomial time algorithm, which was observation 2, brought down the execution time by several orders of magnitude. Finally, adding the minimality optimization brought down the average execution time by roughly a factor of 40. We then used our algorithm in real-world applications. Gator is a domain-specific graphics programming language with novel geometry types that, like the example in the first slide, has automatic type conversions. Incidentally, it's also appearing in OOPSLA 2020. So we implemented this algorithm, verification algorithm, in the Gator compiler and used it to verify real programs. So we used so in our programs, functions were matrices and nodes were reference frames in a graphics program. And the algorithm was able to run in real time, and it caught the bugs we wanted it to be introduced. I wanted to see the algorithm applied to large graphs in a real world situation. So I stepped outside of programming languages and tried to use it on currency conversion graphs, where the nodes were currencies and the exchange rates were the edges. With a runtime that was in minutes, it was able to find inconsistencies, and I accounted for floating point error by setting error tolerance. So ultimately, we've introduced an algorithm for online commutativity verification that handles real-time online addition and works with real applications. Thank you. I can take questions.
Thank you. Any questions from audience?
I have one quick question, which is just if you found this commutativity and consistency in the currency exchange market, are you able to take advantage of that, or what does that mean that there's an inconsistency there?
So I was using an API, and ideally I'd be able to take advantage of it, but I didn't try to do that. I imagine that the penalty on trade, like, isn't there a percent you need to pay when changing currencies? Anyway, I don't see this as a primary application of the algorithm, since I think just searching for negative weight cycles would be a more efficient algorithm for this problem. I just wanted to see how the algorithm dealt with these graphs.
Very cool. Thank you.
So I think I have a question, but I'm not working in this area. So, but when consider about program analysis or static analysis, when we talk about constraint solving, we solve constraints, and if we want to, for example, we want to detect cycles for constraint solving. Normally, we have the embarrassing scenario is we need to detect cycles, collapse nodes, and then do the solving. However, when you try to detect cycles, it also incurs extra overhead. So somehow we always want to perform online cycle detection, then try to solve the constraint graph in a way that is in an iterative manner, so that we can basically can quickly find the cycles or SCCs and collapse them to conduct constraint solving. So any connections between your work and any particular applications towards this end?
Well, I don't know much about constraint solving, to be honest, but in the optimization step, we did have a graph, a constraint graph, if you will, sort of, where there potentially could have been cycles where we would just have collapsed the cycle to one node, and we would treat the entire cycle as one node, and everything coming in and going out would be as if it were going in and out to the same node. I'm sorry, I don't really know how this relates to constraint solving. If you could repeat your question, perhaps explain.
Okay, yeah. So what you're understanding is correct. Basically, try to collapse cycles, then you reduce the size of the graph, then the constraint solving becomes faster. So, but there's it's always the trade-off, because if you try to detect cycles in advance before you do the solving, then you might not have all the cycles detected since you haven't solved the graph yet. However, if you try to solve the graph, detect the cycles on the fly when you solve the constraints, and then you somehow you might incur extra overhead because you try not like you do two things. One is solving the constraint, another is try to search for cycles. So it's always a trade-off, like whether you want to perform cycle detection in advance or you want to do it all together when you try to do constraint solving, follow specific rules. For example, the pointer alias analysis, you try to use a typical Anderson or inclusion based constraint solving algorithm.
I understand. Yeah, we would face the same question in the step, the optimization step. But I guess we didn't look into it very closely because either way, even if we found all the cycles beforehand and collapsed them, or if we solved the constraints and then when we encountered a cycle dealt with them, either way we would have had less asymptotic runtime than the previous step. So that algorithm was v to the fourth, but this constraint solving would be not more time than that. So we didn't really look very closely, but I think that this would be a relevant issue in that step.
Okay, yeah, thank you.
Thank you.
Any more questions? Okay, so let's move to the third speaker. So our third paper is towards checkpoint placement for dynamic memory allocation in intermittent computing. So may I know who is the next speaker? Can you raise up your hand?
Hi, that's me.
Yeah, you can share your screen. Yeah,
All right.
Please feel free to start.
Thank you. Hello, everyone. I'm Nick, and I'm here today to talk a little bit about intermittent computing, specifically some research I've been conducting with my two advisors, Rugis Piscatch from Yale University and Mark Santalucido from Barnard College. Our research is focused on how to add support for dynamic memory allocation on intermittent computing devices with checkpointing systems. And to start off, I'd like to give a little bit of context in the form of energy harvesting devices. And as the name implies, these are just devices that harvest ambient energy from their environment in very extremely small amounts. This could be from multiple sources, solar power, or even something as exotic as radio waves. And the main advantage of these devices is that they eliminate the need for batteries or wired power, which makes them low maintenance and good for inaccessible locations. For instance, for long-running environmental sensors or even space satellites. But the problem with them is that they only have enough power for short bursts of computation. They can't be running continuously. And if we think about a normal program, here we have an example in C where we just count up to 1,000 and then turn a light on. Well, if we lose power somewhere in the middle of that program, then when we regain power, the program will start over from the beginning. So if we never have enough power in a single pulse of power to get all the way through our program, then our program will never finish. We'll just be stuck infinitely repeating the first half of our program. We won't be able to make forward progress. This is called non-termination. So what we'll be talking about in this presentation is how we can ensure forward progress for intermittent computing devices, and then specifically how we can do this for programs that use dynamic memory allocation. And I'll do this in three parts. I'll start off by talking a little bit more about what intermittent computing is, and then the state-of-the-art solution to this non-termination problem, which are called checkpoints, how we can enable forward progress. And then I'll talk about our contribution, which is adding support for dynamic memory allocation to these intermittent computing systems, to these checkpointing systems. So energy harvesting devices are a form of intermittent computing. They aren't on all the time because, like I said, there's so little energy in their environment that they can't actually run continuously. So they have to store up power somehow. And they do this using a capacitor. They charge up the capacitor slowly over time, and then they discharge it in one short burst of power to power the device. Here on the right, we have an example energy harvesting device, and then we have a capacitor that's charging up, and this gives us sort of a power supply that looks like this. Here in the graph, we have the energy level stored in the capacitor over time. On the upward slope, that's when we're charging the capacitor very slowly, and then the downward slope, that rapid downward slope, we discharge the capacitor all at once in a short burst of power. And then that blue region is what we're actually working with. That's where we can do meaningful computation, where we actually run our program. So what we see is we have pulses of power, and we end up only being able to run our program intermittently for a short period of time. So we need to make it so that, like with that non-termination problem, we need to make it so that when we lose power in the middle of our program, and then we regain power, instead of starting over from the beginning, we instead pick up where we left off. And the way to do that, well, first we have to understand why we're losing power, why we're losing progress in our program in the first place. And that's because all of the state of our program, everything from the variables to everything stored on the stack and the registers, is stored in what's called non-volatile, in what's called volatile memory, which is memory that's erased when the device loses power. So when we lose power, all of our volatile memory is erased, all of our state is erased, we lose all of our progress. But what we can do to solve this problem is add what are called checkpoints to our program. And all a checkpoint is it's a piece of code that takes all of this volatile state and moves it over, it saves it into non-volatile memory, which is memory that doesn't get erased when the power is lost. So that way, if we have a copy of our state in non-volatile memory, when we regain power, we can just restore from that copy. Here we have that same C example from the beginning, except now we've added checkpoints to it. We've added a checkpoint inside the while loop, and we're checkpointing every iteration. And all that's doing is it's just keeping an up-to-date copy of our state stored into non-volatile memory. And that way, when we go through a power cycle, when we have a power failure and then regain power, we can run load checkpoint and restore at the very beginning of our program. We can restore from the state saved in non-volatile memory and continue where we left off. All right, so we can fix this forward progress problem, this non-termination problem, by adding checkpoints to our code. So we might be tempted to add checkpoints everywhere so that we always have an up-to-date version of our state stored in non-volatile memory. But it turns out this is very inefficient because checkpoints actually have a cost associated with them. They take time and energy to run. So if we were to put checkpoints everywhere, we would have a lot of overhead from all that checkpointing. So we don't want to place them too frequently, but we also don't want to place them too infrequently, because if we don't actually reach a checkpoint in a given pulse of power, then all of the computation, everything we've done for that pulse of power is lost, because all of the state for that pulse of power is lost. So what we really want is we want to have at least one checkpoint per pulse of power, and ideally right at the very end of the checkpoint, right at the very end of the pulse of power, so that we don't waste any of this energy. Here in the graph at the bottom, we are graphing the available power in the capacitor. We can see that the energy level is steadily decreasing as our program runs because it's using power. And then right at the very end, the energy level is critical, and we checkpoint in enough time to save all of our state. So that way, when we regain power, we can just restore from our checkpoint. Yeah, so right at the end is the ideal placement for our checkpoint. But it's too difficult to place these checkpoints manually, because that would rely on us being able to predict as the programmer where these power failures were going to occur. That's too difficult. So we need some way to place them automatically. And there's two ways to do this. We could use static analysis to place checkpoints at compile time, or we could use some form of power estimation where we try to predict what the energy level in our capacitor will be. And then when we think it's getting low, we can preemptively checkpoint and save all our state. And strategies exist that use both of these techniques, but the problem with existing strategies is that they kind of assume the cost of checkpointing is approximately constant. And the problem with assuming that is that when we add in dynamic memory allocation, which is what we're interested in, then actually the memory usage of our program is constantly fluctuating because we have lots of allocations and then deallocations happening all the time. So our memory usage is fluctuating, and this cost of checkpointing actually depends on what the memory usage is at the time of the checkpoint, because the checkpoint has to move all of our memory into non-volatile memory. So if there's more memory to checkpoint, the checkpoint will cost more. And that means that when we have dynamic memory allocation, actually the cost of our checkpoint is fluctuating as well. So we can't just assume that the cost of checkpointing is constant. So this is what we've been researching, how to have a strategy that efficiently supports the heap dynamic memory allocation under intermittent computing. Here I have an example that illustrates this problem of why we need to take the heap into account when we are checkpointing. This example has both dynamic memory allocation and checkpointing. At the very beginning on lines 2 and 3, we have 2 allocations of 16 bytes each. And then we have 3 possible checkpoint placements on lines 4, 9, and 12. If we look at the first checkpoint placement, we can see that we have 46 bytes to save because we have the 32 bytes from our 2 allocations, and then we have just memory from the rest of our program. Could be memory on the stack or in the registers. So we have 46 bytes, and we'll say that this costs 1,000 nanojoules to save 46 bytes to checkpoint that. Now, if we move on to the next checkpoint location on line 9, we can see that now we only have 30 bytes to save, and that's because we've executed some code between lines 4 and 9, where we've done first a computation using some of this allocated memory, and then we've deallocated some of this memory. So now we have only half the memory that we had on the heap. So we're down to 30 bytes that we need to checkpoint, and this brings our cost of checkpointing down to 700 nanojoules. If we proceed to the final checkpointing location on line 12, we can see that now we only have 14 bytes to save because, again, we've done we've executed more code where we've done another calculation with the remaining memory, and then we've deallocated that remaining memory on the heap, bringing us down to 14 bytes that we need to checkpoint for a cost of 400 nanojoules. If we look at all these costs together, we can see that as we progress through our program, the cost of checkpointing decreases because we're deallocating more and more memory. But we also see that the energy level in our capacitor is decreasing as well because our device is consuming power constantly. So as we reach the end, the power level is getting kind of critical. So a traditional checkpointing system might be tempted to checkpoint before we reach the end of our program, say on line 9. Because it would be worried that it wouldn't have time to get through the entire checkpoint and save all of the state before running out of power. And if we don't get to a checkpoint, then we will lose all of our progress for that pulse of power. So it would be a little pessimistic and place a checkpoint on line 9. But if we actually examine the difference between these 2 checkpoints, lines 9 and 12, we'll see that the cost of checkpointing on line 9 is actually 700 nanojoules, and the cost on line 12 is 400 nanojoules. But the computation in between only costs 200 nanojoules. We have that calculation on line 10 and then a deallocation, and that only costs 200 nanojoules. That deallocation actually saves us energy. So by the time we reach line 12 and we have a cost of 400 nanojoules, we've actually saved 300 nanojoules just by waiting to the end of our program, which is more than the computational cost of 200 nanojoules. We can kind of generalize this to say that anytime we have a deallocation, we're saving energy because remember, under intermittent computing, we have these pulses of power, and we always have a guaranteed checkpoint at the very end of the pulse of power. And that cost, the cost of that checkpoint will vary depending on how much memory is in use when we reach the end of our pulse of power. So by deallocating memory, there's actually less memory for our checkpoint to save, making the checkpoint cost less, meaning we have more energy to do other meaningful computations. So here, that means we can make it all the way through our program. It's always most optimal to place our checkpoint at the very end. It's always optimal. We've actually tried out this strategy with a real world test setup. We ran an experiment where we had a power and energy harvesting device, and then we had a transmitter. The energy harvesting device was harvesting radio waves, and the transmitter was transmitting radio waves to it. And then we varied the distance between the two, and we measured the performance of 3 different programs. So in this graph, we have on the x-axis the distance between our energy harvester and our transmitter, and then we were observing the percent speed up that we saw when we placed checkpoints efficiently, optimally, with regards to the memory usage of the heap, with regards to the heap. So what we actually saw, if we look at the blue and the red line, we'll see that we have 2 different forms of merge sort, 2 different versions of the merge sort algorithm. And we always saw at least a positive speed up. So this is very promising. We always get at least a positive speed up. And then with the brown line, we actually had a best case scenario, which was when it was a very simple program to illustrate this problem, where we had a large allocation and then a large deallocation almost immediately afterward. And in the case of that best case scenario, we saw up to a 25% speed up. And even with the real world merge sort algorithms, when the conditions were right, we saw a pretty dramatic speed up. So on these low power devices, these energy harvesting devices, every little bit of performance counts, and this can really add up over time. So very promising. To sum up our contribution, our key insights were that checkpoints have variable costs when you add in dynamic memory allocation. And because of this, free statements can actually save energy, because then we've deallocated memory, and that means we have less memory that our checkpoint needs to save, making that checkpoint cost less, and then we can use that saved energy to do other computations, make it farther through our program, make our programs more efficient. The problem with our current analysis is that it only handles straight line programs, which means we can't have branching or looping. So the next step is definitely to use some more advanced static analysis, maybe separation logic, to reason about memory in real world programs where they're not just straight line. To sum up the talk, I discussed what intermittent computing is in more detail, and then the state-of-the-art solution to this non-termination problem we talked about in the beginning, which are checkpoints and how they enable forward progress. And then I talked about our contribution, which is adding support for dynamic memory allocation to checkpointing systems on intermittent computing devices. At this point, I'd like to thank everyone for listening to my talk, and then I'd be happy to answer any questions.
Okay, thank you, Nick. Any questions? I think it's very interesting talk. Actually, I have a few questions. So, when you take a look at your example, right? So you mentioned that you are focusing on the dynamic memory allocation, so especially for this work. So imagine if the program were written like some programs may not have a dynamic allocated memory. So I also think that you also need to consider those stack variables, right? So for
Yes.
function calls, like when you have the multiple methods, so there's a call chain. In that sense, I'm not quite sure whether you have considered inter-procedure analysis or inter-procedure checkpoints rather than just a single method.
Yeah, I don't know too much about that, but I think, yes, we definitely need to consider the stack. Actually, our same strategy could be applied to the stack. The idea is pretty much that dynamic memory allocation provides more of this fluctuation, which means we can have more of a speed up. there's more opportunity to improve the efficiency. But yeah, we could definitely do the same thing with the stack. Does that answer your question?
Yeah, I think partially, because stack, if you consider stack variables, then the case is somehow simpler, because after executing a method, a program method, a function, then all the stack variables, once returned back to its caller, then the stack variable inside that method will be destroyed. So
Right.
in essence, it's similar as your free. Because you don't need to checkpoint lots of things or lots of values once after a method has been executed. So another, I think another question I'm interested in is, because the device has energy, right? So in your example, for example, when you reach line 12, if you need to predict whether from starting from line 9, when you execute to line 12, the battery is still, you still have enough battery to or enough energy to execute from line 9 and line 12, right? So there's, you need possibly a prediction mechanism to say, or a model which say whether I can go from line 9 to line 12, then you can decide whether line 12 is optimal or not, right? If you can't execute, you can't reach line 12, then you can't say this is optimal placement, right?
Well, the idea with this example is that it's always optimal to reach line 12, because by doing that free, by having the deallocation, we're saving energy, because then our checkpoint, so we only have a finite amount of energy in each of these pulses of power. So if we can make the checkpoint cost less, then we can use the rest of that energy to do more computations. So if we free, we basically are freeing up energy. If we free 300 nanojoules, it means that we always have, we're always able to get through that calculation, because we're leaving a bit of a buffer at the end of the pulse of power so that we can get through our checkpoint. So we always know we have a little bit of energy left. And then if we can make the checkpoint cost less, then we can proceed to line 12.
But this has to be known in advance, right? Before you reach line 12.
Right.
When you're sitting at line 9, you have to make sure you have enough energy that can do the computation and then reach line 12, so that you can place that checkpoint at line 12, right?
Right. So we have to have some sort of static analysis to determine, blocks of code where it always doesn't make sense to checkpoint in that region, because they'll be followed by a deallocation, making the computation not cost anything.
But I guess there's need a runtime monitoring as well. You have to constantly monitor the energy to make sure it's enough energy that you can reach to an optimal checkpoint place, right?
Yeah, so we're thinking about combining static analysis with existing runtime models, because they do have, you can measure basically the length of these pulses of power, and then you can, after you've gone through a few pulses of power, you get a pretty good estimation of how long they are, and then you can predict when a power failure is imminent. And
yes.
Yeah, and then we would inform that estimation with some form of static analysis.
Yeah. Okay. Yeah. Very good. So that's all from me. Any more questions? Okay, yeah, so we probably end this session. So we thank all the three speakers, and we will come back, I think, in 15 minutes for our keynote, which will be given by Manu. So see you in 15 minutes.
Hi, Manu.
Hi, Hakchu. How are you?
Could you try
Hi, Manu.
to share your screen?
Sure. One moment. So can you see?
Yes.
Yes, good.
Okay, great. Should I keep sharing or?
Yeah,
Yes.
it's okay.
Yes, please.
So we can
It's okay?
wait for a few minutes, then we can start.
Okay, so should I leave the sharing on or turn it off, or it doesn't matter?
It doesn't matter. Should be fine.
Okay. I'll just start it again in a couple minutes then.
Yeah. What's the time now? That you said?
It's almost 9 o'clock a.m. on Thursday, the 19th.
Okay. Yeah.
It's late evening, yeah, or night.
Well, actually,
I'm trying to remember. Are you
it's
16
very,
hours
very
ahead?
early morning.
Oh, okay.
I think it's
quite
2
bad time.
2 a.m.
2 a.m.
Hangzhou time and 4 a.m. here at my side in Sydney.
Oh, wow. Okay. Sorry about that.
It's okay. Yeah, I think it's not the time is not that good for Asian and Europe audience.
Yeah, a lot of events are being mirrored, I guess. So but this one, I guess we didn't do it that way. I could have pre-recorded the talk, I guess, but I was actually still working on it even yesterday, so that would have been tricky.
Would you like us to record?
Oh, certainly, yeah. I was
record.
hoping this would be posted on YouTube afterward. If you guys are
Yes.
doing that for.
Yeah, we will first send you the video. Then, if you are okay, then we post.
Okay, that sounds good. How did the workshop go so far?
It's okay. I think it's going well.
Great.
Yeah.
Are you all trying to submit anything to PLDI? That's the only tricky thing. The deadline is coming up. Working on that too.
Are you planning to submit a paper to PLDA?
Yeah, one resubmission. So, but still some work to do. Okay, I guess I'll go ahead and share now.
Yeah. And also, I think Manu, your talk gonna to be live stream, so I think it's going to be they don't need to like join the Zoom. They can watch you.
Yeah,
talk.
they can watch on YouTube.
Yes.
Yeah, I noticed that. So I sent some people the link and said they could watch if they wanted to.
Yes. Hajun, would you like to do the short introduction before Manu start?
Okay, shall we start?
Sure.
Okay. Let's start the last keynote session. So let me introduce the speaker, Manu Sridharan. Manu is a professor at the University of California, Riverside, and he previously worked at Uber and developed a static analysis system there. And before that, he worked at IBM Research and Samsung Research. And today, he'll talk about his recent work about using pluggable type systems. So Manu, would you please begin?
Thanks so much. So thanks everyone for watching. Today, I'm going to be talking about some of my recent research on moving fast with high reliability using pluggable types. And this has been done with a bunch of collaborators, my students, Manli Ran and Nargis Shadab at UC Riverside, Lazaro Clapp at Uber, Subarno Banerjee from University of Michigan, Martin Kellogg and Michael Ernst from University of Washington, and Martin Schaaf from Amazon. So let's start with some background. What are pluggable types? This is a technique that's actually been around in various forms for quite some time. The idea with pluggable types is that you can extend your compiler with additional type checking for new kinds of properties beyond the kind of compilers that come built into the language like Java. And we're going to be focused in this talk on the Java language. And the way that you can add type annotations is via, in Java, the Java annotation system, though that's not fundamental, you could do it via comments as well if you wanted to. So in terms of pluggable types from Java, one of the main original papers on the technique was published actually in 2008 in ISTA, and it's been embodied in the Checker framework since that time. So let's take a look at an example of how pluggable types work. And we'll do it with kind of the classic or maybe most common use case for pluggable types in Java, which is trying to prevent null pointer exceptions. So here's a simple code example. We have a logging routine that just prints out the two-string representation of an object. And in this other method, foo, we're calling this logging routine with null, which is a buggy way to do things. So with a pluggable type system for nullability, the typical assumption is that if you don't write an annotation on a field or a formal parameter, the tool assumes that parameter to be non-null. So here, the programmer didn't write anything. We'll assume that this parameter should never be null, and immediately we'll report an error because that parameter shouldn't be null, and we see at this call site that we're trying to pass in null. So let's say that we want to allow passing null to this routine. What you can do is add a type annotation. Here it's written nullable on the parameter. So this is telling the tool that you are allowed to pass null to this function. But now you'll get another error because the tool observes that we're dereferencing this variable x that's been marked as nullable. So this can lead to a null pointer exception. So we can get rid of this error by adding a null check in the log routine. So here, if x is null, then we just return. And now the tool will be able to verify that this code is free of null pointer exceptions. So this kind of technique has been embodied in the Checker framework since at least 2008. So we're doing new research in this area. So what's new right now? So my research has been broadly focused on finding bugs for many years. And before recently, I was using different kinds of approaches to attack this problem, primarily whole program static analysis and dynamic analysis. And I thought it would be interesting to kind of go through some of the trade-offs between these techniques for bug finding to see where pluggable types can play a nice role. So if we look at whole program static analysis, and let's just go left to right here, So we don't need annotations, right? Oh, sorry. We don't need annotations. You can just analyze code as is and try to find bugs in it. And that's a big advantage. Say, if you're trying to analyze code from other companies or code on the internet, we can cover all the paths. So in you can potentially build a verifier that catches all bugs of a certain class. On the downsides, you do get false positives, potentially a significant number, depending on how your technique works and whether you're trying to verify a property or just find bugs. But I think the bigger issues, honestly, in practice are error messages. So sometimes errors can be good, but if you talk about complex whole program properties, very often it's extremely difficult to explain the error to the programmer. There was a great discussion of this in the CACM 2010 paper from the Coverity folks about how they had to turn off various error checks just because the messages were not understandable. And also, overhead of this kind of analysis can be quite high. So there have been various techniques recently to try to do incremental and modular analysis rather than trying to do things at a whole program level. But getting results, complete new results after a change can still take on the order of minutes to hours for large programs. So now let's look at dynamic analysis. And the key advantage of dynamic analysis is that you don't get false positives because we've executed the program and we've observed the bug actually occurring. But there are downsides to dynamic analysis. So you're not covering all the paths. Fundamentally, you're going to have this issue that you might miss bugs because you didn't have the right inputs to expose them to your analysis. And then in terms of error messages, they're often clearer than static analysis because you have a concrete execution path that witnesses the bug. But if it's a whole program property tying together many different source files, I would argue it still can be hard to understand what's going on in some of these issues. And overhead can also still be high, depending on what kind of analysis you're doing. And dynamic analysis can often suffer from difficulty in deployment. If you're trying to test a system kind of in a production configuration, you're going to have to find a way to get your instrumented code or your monitor running in that system. And often in practice, this can be challenging. So where do pluggable types fit in? On many axes, I would argue that they have advantages over these other approaches. So in terms of error messages, I think that pluggable types can give you clearer error messages than either static or dynamic analysis. The user does have to understand what the type system is doing, but once they do, the key advantage here is that the errors often only relate to code in a very local scope, say within a single procedure. Now this assumes you're not doing things like whole program inference, which we don't really do in the techniques in this talk. If you did do whole program inference, then you start running into the same issues that you do with whole program static analysis. The other thing is that, again, if you're doing limited global inference, your overhead can be quite low. This requires some proper engineering of your tool, but the overhead should be on the order of the same cost it just takes to compile the code, which is much, much lower than a whole program static analysis. And also in some ways, lower than dynamic analysis in that once you're running your code, you're not adding any overhead. So the key downside, I would say, or question about pluggable types is right here. Because we're trying to avoid doing whole program analysis, developers need to add some annotations in order to get these systems to work. So I think that's the key question here, is that will developers actually write these annotations that are needed to make these systems work? And for a long time, I think the assumption in our community was that this is actually quite impractical. that developers just want to ship features, and if you ask them to do any extra work to achieve a higher level of safety, they're just going to ignore you or blow you off. But I think things have changed recently, and one of the key driving factors in this change are deployment models for mobile applications and what happens when you have a crashing bug in a widely used mobile app. And obviously my experience is from Uber, where I was working. So the issue with bugs in mobile apps is that it can take quite a long time to deploy a fix if you have some critical bug and you need to get your fix out to users. So if you have a good deployment system on your backend servers, you can potentially deploy a bug fix once you've written it on the order of minutes to hours. You just need to update the software on the server, and then your users are using that new version of the software without any change on their device. In contrast, when you have a bad crashing bug in a mobile app, it can potentially take days to even weeks for all your users to end up on the new version of your app that fixes that bug. This is because of issues like getting approval in app stores and then waiting for a user to explicitly do an update. They might not need to be on a good internet connection to download the new version of your app. So this is kind of out of your control, and this can take a while. So a key lesson that I learned when working at Uber on these kind of apps is that if you have a bad enough cause of crashing bugs, developers will work with you to annotate their code to avoid crashes. So we had a lot of success at Uber with these kinds of techniques. And another advantage here that developers really like is that if you can get your pluggable type system running inside the compiler with low overhead, they enable what's called a green master, where basically if you check out the latest version of the code and you run your checker on that code, it should report 0 warnings. And we did actually get to that point for more than one type-based checker at Uber. So you can run these things on every build. They run fast because they're modular and incremental very naturally. And in my experience, achieving this level of checking with pure static analysis is very difficult. Either you just can't block the build on these errors, so developers are free to commit their code even if the static analysis is reporting issues, or the static analysis is so costly that you can't even run it on every build, so you need to run it maybe overnight. So there's a lot of potential for pluggable types to yield greater software quality when deployed, but there are some key challenges that need to be overcome. So you need to have a low false positive rate for sure. So if most of the errors being reported by your tool are false positives, again, developers are just going to ignore you. You also need to have a low annotation burden. And this is a trade-off, right? You can't take it to 0. Developers are going to have to write some annotations, but it has to be low enough that, given the significance of the bugs that you're catching or eliminating, developers decide that this is worth it. And finally, you need to have low enough build time overhead. So if your tool is still taking, minutes to hours to run, then it's not going to be deployable in this kind of green master scenario that we would like. So in the remainder of this talk, I'm going to present 3 different projects, recent projects in this area of pluggable type systems that we've been working on. I'll first talk about Nullaway, which is the work that we did at Uber on practical type-based null safety. Then I'll talk a bit about some more recent work on verifying complex object initialization patterns. And finally, I'll talk about some work that's still in progress on using similar pluggable type system techniques to prevent resource leaks in Java programs. So let me start by talking about null away. So when we started this work at Uber, the motivation was exactly what I mentioned before, app crashes. Uber really needed null safety for its Android apps. Null pointer exceptions were causing a significant percentage of crashes in Uber's Android apps. And as I mentioned, there are existing tools for doing this kind of type-based checking. So the first tool that was tried at Uber was a tool called Eradicate, which is actually part of the Facebook Infer system. And it worked well in terms of they invested a lot of effort, and actually using that tool got the null pointer exception rate way down. So it caught a lot of bugs. But there were some downsides. So this tool was still too slow. It couldn't run on every single compile, partly because it ran kind of outside the compiler, and also it ran on a separate intermediate representation than what the compiler was using. So they were able to only deploy it on continuous integration, and this led to a bad developer experience. Developers were annoyed that they had to wait on this tool and fix all its bugs before they could commit their code. Also, it caught many bugs, but it still missed a few. So we also tried the checker framework, and there were still issues with the build time overhead being too high. And also, we found that there were too many false positives. And here, what I mean was that in some sense, the annotation burden was too high. You had to add a lot of annotations, but those weren't actually catching more real bugs in our experience. So the goals that we had when we decided to build null away was to try to make it fast, try to catch most bugs. Note that I don't say all bugs. We're willing to compromise in some areas in order to make the tool usable. And we wanted to have a very low false positive rate. So one of the main techniques that we used to achieve these goals was making various trade-offs in terms of how sound we wanted the tool to be. So a nice way to phrase what our high-level goal was we wanted to have no false positives in practice for checked code. And let me talk a little bit more about what I mean there. So our strategy was to introduce some unsound assumptions in places where we saw that the false positives were too high or the annotation burden was too high. We said, let's try being unsound for this construct. But then, as we deployed the tool, we could look at crash data from the field, from our deployed apps, see what was actually causing null pointer crashes, and then tweak these assumptions to try to eliminate as many of these crashes as possible while still keeping the tool usable. So where we ended up with was a few interesting techniques. We had a novel algorithm for checking initialization, which is unsound, but quite practical in that it seemed to eliminate, at least in the Uber code base, all the initialization bugs that we saw. And we had unsound handling of certain other features. I'll give an example on the next slide. The other key thing that we did was in our handling of third-party libraries, we found that the only way to do this reasonably is to handle them optimistically. This means that basically we assume that if you had a third-party library and it wasn't annotated, that it was not going to be the root cause of null pointer bugs. So this doesn't sound great, but we found that the alternatives were worse. So if you try to do a pessimistic handling of these third-party libraries, assuming basically that they can wreak havoc whenever you pass in a null value and that they might always return back a null value to you, that just has an impractical annotation burden. We couldn't get that to work in practice. There is a downside here, which is that this is still probably the main cause of bugs, null pointer bugs that are missed by our tool. And we have some ongoing work on trying to do better for these kinds of libraries with a bit of inference. So let me give you an example of one of our unsound assumptions. And this is around method purity. So let's say we have this class foo holder with a field foo that is nullable. And let's assume also that we have standard and getter and setter methods for this field. So now let's look at this code. We get some foo holder object, and we check if the foo field is not null. And if it's not null, we're going to call this set foo method with null. So that's going to set the field to null. And finally, we dereference the field, which causes a null pointer exception. Okay, so this is buggy code, but our tool is not going to emit a warning here. And the reason is that we assume that this set foo method is pure. So we unsoundly assume that it's not going to have side effects and it'll act deterministically. So clearly this is unsound for examples like these, but we found that in practice, this kind of code occurs very rarely. It was just not at all a cause of the real world null pointer exceptions that we were seeing in the field for our apps. So in terms of low overhead, there wasn't really any magic here. All we did was sort of engineer the fastest type-based null pointer checker that we could. So we built it directly as a plugin to the Java compiler. We based this on ErrorProne, which is a great bug finding framework for Java that was written by Google. We did leverage the library from the checker framework for data flow analysis, but we didn't use any other general type checking framework. We built everything from scratch, and we use standard techniques to speed things up. So we tried to be lazy. The data flow analysis is the most expensive part of this tool. So we tried to only run it when absolutely required. And we were very aggressive about caching results so that we didn't do this expensive work more than was necessary. So let me talk about some of our results. So in terms of overhead, this was a big win. On average, we only saw about a 15% overhead over just compiling your code. So that's pretty low and much lower than these alternate tools. And it's low enough that you can run this on every single build. And that's what Uber still does for all their Android code. Anytime you compile it, nullaway is running. So then there's a question of how are we affected by these unsound assumptions? And what we did was we looked at 30 days of crash data across all of Uber's Android apps and looked at all the null pointer exceptions and tried to figure out what was the root cause here? Why did nullaway not catch this? And what we found was that we had achieved our goal. In terms of the code that nullaway was fully checking, so excluding third-party libraries, none of our unsound assumptions actually led to any null pointer exceptions. So the remaining causes of the actual exceptions were optimistic handling of libraries or bad suppressions. So nullaway has a way for a developer to just suppress a warning and say, please just ignore this. And sometimes those suppressions were wrong and leading to crashes. And finally, there was some complex reflective code that nullaway did not handle. So we did another study where we looked at 18 open source benchmarks and we compared the additional issues that were discovered and reported by the checker framework as compared to what was reported by nullaway. And in this study, for all the additional issues, we studied them and they did require some more annotations to type checks, but there were no true bugs that were root caused to those issues. So that just gives another piece of evidence that the unsound assumptions that we made in nullaway are reasonable. So that's all I wanted to say about nullaway. You can go read our FSE 2019 paper to get more details, or I encourage you to just try it out. It's available on GitHub. It's pretty popular, both in open source and in industry, and it's still very much supported. So try it out and let us know how it works for you. Okay, so next, I'm going to be talking about more recent work on verified object construction. So in this work, we're using a pluggable type system to verify some complex object construction patterns that we see a lot in modern code. So where do these patterns come from? Well, the issue they're trying to deal with is that in Java, objects that you build often have a mix of properties that are required and some that are optional. So here's a simple example. We have a user identity class. It has 3 fields, name, ID, and nickname. And both the name and ID field are required, but the nickname field is optional. You can either provide it or not provide it. So how do we typically construct objects in Java? Well, we use constructors. So here, you could provide 2 different constructors depending on whether or not the client wants to provide a nickname. And let's say that we have these constructors and some client tries to build an invalid user identity object, see, just providing a name, but not an ID. Well, as you know, the compiler is going to reject this. You'll get a compile error because there's no constructor signature that matches just passing a single string argument in. So constructors are the standard ways to build objects. And the pro here is that the compiler will do some verification that the arguments are sensible and will reject your code if you pass in the wrong types or the wrong number of arguments. But there's a bunch of negatives. First, as you saw, we had to define 2 different constructors in that case. And you have to write each of these by hand. And as the number of optional properties grows in your class, the number of constructors you have to write for all the different combinations will start growing exponentially. So that's definitely a problem. Also, can argue that when you're doing constructor calls, the arguments are positional. So in this previous case, we saw that we had a string name and a string nickname. And if you look at a call to the constructor, you just see 2 strings being passed, but there's nothing in that code to tell you which one is the name and which one is the nickname. And as you add more and more arguments, it gets harder and harder to read the constructor and know what arguments are getting passed for what purpose. So this has been an issue in OO code for quite a while. And there's like a well-known design pattern that helps you build more readable code in these scenarios. It's called the builder pattern. So here's our same user identity class written with a builder. So now we have an inner class user identity builder, and we have different routines to gradually build up the state of our user identity. So we have a method to set the name, we have a method to set the ID, we have a method to set the nickname, and when you're all done, you can call this build routine, and that will return your final user identity object. And very often, this code is written with each method returning the builder itself. And so you can write your construction code in this nice fluent style, right? So here, I create a builder, and then I invoke name and ID to set the name and ID. And finally, I call build to get my final user identity object. So this looks much nicer. As you can see, it's very clear what purpose each parameter is getting passed for. So this is flexible, easy to read. We avoid this issue with having to write an exponential number of constructors. And in fact, there are various code generation frameworks like Project Lombok or AutoValue that, given a Java class, will automatically generate all this builder code for you. So that's really nice, but we have a downside here. So now let's think about our erroneous pattern again, where we wrote this code, but we only passed a name. So unlike the constructor case, this code compiles just fine. So then the question becomes, what's going to happen at runtime when you write this code? I think the best case is you get an immediate runtime error telling you you're constructing an invalid object. So at least you know something bad happened, but still we're a lot worse off than the static analysis case, where we were detecting all of these issues right in the compiler. Even worse, sometimes you don't get an immediate error, you just end up with a malformed object. And we saw that this can even lead in some scenarios to security vulnerabilities when you don't invoke the right methods to construct your objects in a secure fashion. So this is a big problem. Although we have flexible and easy to read code, we don't have any kind of guarantee that the required arguments are actually provided. And this is something that developers hit all the time. You can see all these issues on the project Lombok GitHub related to this. And in fact, the lead said that, we get this feature request every other week, and the feature request being detecting missing required property calls at compile time. And that's exactly what we do in our approach. So we've built a system that gives you static safety for uses of the builder pattern. And in fact, it's quite a bit more general than that, which I'll talk about in a few slides. But you still get to keep the advantages of the builder pattern as opposed to constructors, the easy to read code and not needing to define an exponential number of constructors. So how is it that we check this? Well, one way you can think of the correctness of using the builder pattern is as a type state property. So if we have a builder object, you can imagine it being in different states depending on which of the required setter methods you've invoked. So we start in a start state right here, and then if you invoke both the name and the ID functions in either order, you end up in this accept state where you're allowed to call build. But if you try to invoke build early, that transitions to an error state because you have not invoked all the required property setting methods before you called build. So this is great. We've got a type state automaton here. We have decades of work on type state analysis. Why don't we just use an off-the-shelf type state analysis system to try to solve this problem? Well, here, the problem, which I discussed before about whole program static analysis, is that this kind of analysis is expensive. And the root cause of the problem is that general type state analyzers rely on doing a whole program alias analysis in order to soundly handle arbitrary type state properties. So we wanted to avoid doing this kind of analysis for all the reasons that I outlined before. But we had an insight about how this type state automaton looks. And the insight here is that the transitions only flow in one direction. So once you have a builder object that has reached the state where you can call build because you've invoked all the required methods, you never have a transition like this purple transition here, which takes you out of that state and therefore means you can't invoke build anymore. So once you get to the state where you can call build, you stay there. You never transition backwards. So this is a type of type state property we call an accumulation property. And it turns out that if you're doing an accumulation analysis to check this kind of type state property, you can do something much simpler than what you have to do for checking arbitrary type state systems. And these accumulation analyses are similar to some previous ideas in the literature, in particular work on heap monotonic type states from Fondrick and Lino. So what are the advantages of accumulation analysis? Well, one key, probably the most important advantage, is that it's always safe and sound to under approximate. And in particular, you can completely under approximate your reasoning about aliasing. You don't need to do any alias analysis at all to build a sound accumulation analysis checker. And let's look at an example to see why this is true. So here we have a builder B, and we invoke name directly on B, but in order to invoke the required ID function, we do it through an alias B2. So now what's going to happen when we check this call to build at the end? Well, the worst case here actually is that we get a false positive. If you don't track the aliasing, your tool will think that ID was never invoked. But in the case of accumulation properties, that just means that you might think that a legal operation is in fact illegal, which leads to a false positive, but it does not lead to unsoundness. So this leads to this really nice way to design tools. You can build a basic sound tool with no alias analysis at all. And then as you apply it to code bases, you can add targeted reasoning about aliasing to bring down your false positive rate, but never compromising on the soundness of your tool. Another very nice thing about accumulation analyses is that we can implement them modularly, for example, as a pluggable type system. So let me show you how that looks for this case of builder patterns. So we need to write some annotations. So here, for the build routine, we write this called methods annotation. So what this says is that for whatever object you're passing as the this parameter to this function build, you need to have called the methods name and ID on this object already before you get here. One nice thing is that for the frameworks I mentioned before, like Lombok and AutoValue, that are generating this builder code for you, we've actually built integration so that we can automatically generate these specifications also. So we can figure out what methods are the required ones and then automatically reason in our tool about what called methods annotation should be present on these build methods. So in most cases, developers don't ever have to write this unless you're writing your own builders. And I want to note here that I've been talking a lot about object construction and builder patterns. So sorry, what this called methods annotation means is that these methods must have already been called, as I noted. But really, this can express any kind of pattern of the form always call A before B, which I think we've seen a lot in many scenarios. And so this checker is actually quite general, and we're continuing to explore what other interesting properties we can check with this technique. So now that you have these specifications about which methods need to be called before other ones, we need to verify the specifications. And we do this with a called methods verifier. One thing it does is a standard subtype checking at assignments. So we define a subtyping hierarchy where type is a subtype of another if it has more called methods. So in other words, that will ensure that when you invoke this method, whatever you're passing in as the receiver should be a subtype of called methods of name and ID, which means that you can have invoked more methods like nickname on that object, but you should definitely have name and ID there. So this is built into the checker framework. We didn't have to write any code here. So this ensures compatibility at all kinds of assignments and also handles method overriding soundly. Within a procedure, we also do flow-sensitive inference of these called methods types for locals. It's basically tracking what methods are called on a particular expression. So as an example here, if we have a builder, initially, it won't have any methods called. And when we see a call to name, we will update the type to have name in it, and similarly for ID, so that we can verify this call to build. So that's a high level of how this tool works. And I mentioned that we didn't have to do any alias analysis for soundness, but we did find one pattern, which I've already showed you, where we do actually need some alias reasoning for precision, or we get too many false positives. And that's this kind of use case where you're invoking these APIs one after another in a fluent manner. So if you just apply the technique I mentioned before, you're going to conclude that the only method invoked before build is ID, because, and you're going to reject this code. And the main reason is that the tool doesn't know that the object being passed in to ID as the receiver is the same object that's being returned, right? That we're threading the same builder object through these calls so that we can accumulate all these methods on that same object. So we needed targeted alias tracking for these kind of fluent APIs. And I'm not going to get into details, but we did this with a separate type-based approach. So let me just briefly cover some results here. One experiment we did was to study a class of security vulnerabilities, AMI sniping vulnerability, on an industrial code base. So we ran our checker on a significant amount of code, over 9 million lines. We found 16 vulnerabilities with only 3 false warnings, and only 34 annotations had to be added in order to do this. So this was quite a good result in terms of overall effectiveness. We also looked at builder patterns based on these projects, Lombok and AutoValue. So here we looked at 5 projects with about 200,000 lines of code. And we were able to verify over 600 calls. And we found 1 true positive bug. Here we had to add some more annotations than before, 131. Sorry about that. I do think that many of these annotations could be inferred automatically, and that's some ongoing work that we're doing. And we had a few false positives. We got this great comment, though, from an engineer on one of these projects, and they actually fixed the bug that we reported. So that was pretty gratifying. So this tool is also available. It's actually now available as part of the checker framework. So I also encourage you to try this out. It's called the called methods checker. And like I said, this can really check any property of the form, always call A before B. So you don't just have to use it for builders. If you find a cool new use for it, please let us know. So in the remaining time that I have, I want to talk just a little bit about an ongoing project we have on applying these pluggable type techniques to doing resource leak detection. So what are resource leaks? Let me just explain it by an example. Here's some code that's adapted from the Apache Zookeeper project. And in this code, we're creating socket objects. And a key thing about sockets is that they have a corresponding underlying operating system resource. And in order to ensure that resource gets released, you need to call close on this object before it becomes unreachable. That's the only way to ensure that this resource is released in a timely manner. So the problem in this code is that this SO timeout function can throw a socket exception. And if that exception gets thrown, we're going to lose the last reference that we had to this socket, and the underlying resource is going to get leaked. And these kind of issues can turn into serious bugs because you can deplete system resources. So maybe even other programs running on the same operating system won't be able to open a socket or a database connection. This can degrade performance. It can even turn into a denial of service attack. If someone knows how to send a request to your system that's going to leak a resource, they can just do it hundreds of times. And this is also really hard to test for, because if you leak 1 socket, maybe you don't notice. But if you leak 10,000 sockets, then you're definitely going to notice. But certainly writing unit tests for that kind of behavior is pretty difficult. So there are many existing approaches to try to prevent or detect these bugs. Java itself, in Java version 1.7, introduced a new try with resources construct. So you can write your code like this, and if you write it this way, the socket will automatically get cleaned up at the end of this block. So this is great when it applies, but it's limited for one reason, is that the resource has to be closed in this kind of static scope, right? So I can't take my socket and return it from a function very easily or store it in a field. We've seen a lot of code where you can't just immediately apply try with resources to fix the problem. Again, you could try to use type state analysis. There's multiple papers in the literature that use type state analysis to detect these kind of resource leaks. But again, we have the same problem as before. Now we're in the world of whole program alias analysis, and this can take many hours on larger benchmarks. So our observation is that if you squint your eyes the right way, leak detection is actually one of our accumulation properties. So here's an automaton for a simple maybe file or a socket where once you open it, you can write to it. And then you close the socket. And if you try to write to a closed socket, you get an error. So how can we express this issue that you need to close this socket before it goes out of scope? Well, you can just add going out of scope as a transition or an operation in this automaton. So now it's clear that before you exit or go out of scope, you need to call close. And this property of call close before you go out of scope is exactly similar to the called methods properties we were checking before. It's an accumulation property. So we've been working on a checker for this. And the property, and we're trying to check here, we write it as must call, right? So you can write this annotation on a type, and it means that you have to call all these methods before any object of this type goes out of scope. And you can see this doesn't talk about resource leaks. Just like the called method system, this checker is going to be more general, and it can handle enforced calling of any method on any type. We have a checking algorithm that basically extends the called methods type system. We have to infer these must call types for expressions, and then we do a simple data flow analysis to track where expressions might become unreachable, so we can do this check that the right methods have been called. So again, we're in accumulation analysis, so that's really all you need to do to build a sound checker. But we found that you get many false positives, and we're still working on bringing this false positive rate down by doing some targeted aliasing reasoning. And one system that we've come up with is kind of a lightweight version of ownership tracking, which we've seen in a lot of academic work and also in real world programming languages like Rust. So here, we're creating a socket in this code example and returning it. And at the end of this method, S goes out of scope, but we don't want to report an error here because it's really the caller that's responsible for closing this socket. So you can think of this as a transfer of ownership from this S variable to the caller and wherever it stores the return value. So what we try to do is track an owning pointer. That's the pointer responsible for satisfying this must call obligation. And we perform ownership transfer at certain assignments and calls. But unlike other ownership type systems like in Rust, we don't need to invalidate a pointer after ownership has been transferred, because we're only going after this must call property. We're not trying to prove something like, eliminating use after free errors, which does require invalidation. And so we want to reduce the annotation burden here. So we try to have some good defaults, but you can override them with your own annotations. So just briefly, preliminary results are that this analysis scales quite well. It's running in minutes on huge programs as opposed to hours. We have found a bunch of true positive bugs. We're still working on handling certain key coding patterns that we've observed, like storing resources into fields, and also wrapper types, things like buffered input stream, where you can either close the input stream that you've wrapped or the wrapper. We have some ideas on how to handle these cleanly, and this issue has come up in previous work like that of Torlak and Chandra on checking resource leaks with static analysis. So got a lot of ongoing work that I think would be also quite cool to do in the future. We're working on better type inference and introduction. We want to make these systems easier to adopt. So inference can help a lot there. And I think there's a lot of potential to even do things like automatic fixing of bugs, automatic introduction of suppressions to make these systems much easier to introduce. And we have a lot of ideas for more applications of accumulation. In particular, if you look at the specification mining literature, a lot of mined specifications involve these always call A before B kind of properties. So could we connect the specification miner with our checker and very quickly, check these properties or check which ones are likely to be real versus not? I think that could be quite cool. So in conclusion, I've argued that these pluggable type systems are increasingly viable in the real world, particularly because developers really want to prevent bad crashing bugs, and they'll write annotations to do it. And then I talked about null away for fast and practical null safety, and accumulation analyses for doing lightweight modular checking of type state properties. So thanks so much. I'm very happy at this point to answer any questions.
Thank you for
Thank you
great
very
talk.
much, Manu. So it's really nice talk. Any questions from the audience?
Yeah, Manu, thanks for the excellent talk. I had kind of maybe a thought or a point for discussion perhaps than a question. So for the null away work, you had mentioned that the third-party libraries are kind of considered optimistically. And I was wondering if we could kind of use a big code approach here. That is, look at lots of uses of these third-party libraries. And if you find patterns where the return values of those third-party APIs are being checked against null, then, and if you find sufficient evidence of this, then you can automatically decorate those return values as nullable. And you can kind of, I mean, it's not necessarily a perfect solution, but it can kind of get you closer to the final solution of trying to get everything annotated. And maybe, I mean, that one seems a little bit more immediately realistic. There may be similar things that you could do for the other checker framework stuff that you mentioned about something should be called before the other and derive some patterns based on those. But yeah, thoughts on that?
Yeah, I think that's a fantastic idea. So already null away is architected in a way that a user can provide their own models of third-party libraries. So it's easily extensible with whatever third-party library models you want to provide. So I think we've done a little thinking about doing analysis at the bytecode level to try to discover, very obvious patterns. Like if you pass a parameter to some third-party library and that library routine immediately dereferences the parameter, that's strong evidence you don't want to pass null as that parameter. But I think big code is just, yeah, that's a really good idea. If you can find enough users of these libraries, probably you can get some quite strong evidence about when, say, a library routine might return null. And then if you built such a tool, the resulting specifications should be very easy to plug into null away. So I think that's a great idea and very much worth pursuing.
Cool, thank you.
Thanks.
Any more questions? Manu, I have a question because I haven't used Norway yet, but I was wondering if someone like maintaining a legacy code, then how we use Norway for like writing annotations? What would be the best solution? Like for some of the programmers may not like written this data this code base. What would be the best way for them to use this tool to write effectively the annotations?
Yeah, that's a great question, and it's an important problem in practice. How do you adopt this tool when you have a big legacy code base? So Nullaway has a lot of features that make it easier to adopt incrementally. So you can set various configuration flags to say, for example, only this set of packages should be treated as annotated, and then treat all the other code as if it weren't annotated, like a third-party library. So that lets you incrementally get some of this benefit as you annotate more and more packages. You don't have to do your whole program at once. You can even do it down to the individual class level if you want to. But beyond that, we have an active research project on trying to do better inference for Nullaway. So it's a tricky problem, but we believe that, you know, some significant part of the work of annotating a third-party library maybe annotating, you know, this legacy code could be done automatically. Or at least maybe some of the grunt work can be done, even if some of the really tricky problems can't immediately be solved. So that's work that we're actively working on, and I hope to have more results to present to you on that soon. But that's the solution for now is you can adopt it kind of incrementally, go one class or one package at a time, and we're hoping to have some better inference soon.
Okay, thank you. Yeah.
I have a similar question.
Sure.
So I think the idea of the accumulation analysis is quite interesting. And in the verified object construction, you mentioned that only 34 annotations were needed from 9 million lines of code base, right? Is that right?
Right.
34.
Right.
So can you say that, is that set of annotations in some kind of optimal, or so I was wondering how developers know where to insert those annotations into source code.
Right. So it's a good question. So the only kind of inference being performed by that system is intra-procedural. So we only do inference within a method, and that means that whenever you add an annotation, hopefully it's pretty clear that it needs to occur at a certain procedure boundary. So in particular, what kind of annotations would you need to add for that system? They come in when you're taking one of these builder objects and you're passing it across procedure boundaries, right? So maybe you're passing it to a helper routine, which does some of the initialization, or you're returning it from a function after some defaults have been set. And it's at those places where you need to add one of these called methods annotations, either on the parameter or the return value, to tell the tool, you know, that at callers, you can assume that these methods have been called. Or we also have a way to express a post condition. So after you invoke these methods, all these other properties will have been set on the builder. So because we don't do whole program inference, I think that there's less of an issue of trying to figure out, oh, where is the optimal place to put this annotation. There tends to not be a lot of choice in my experience. There's basically one place to put it. And because these cases are pretty simple, that's why I'm optimistic that better inference could reduce this burden even more.
Thank you.
I have another quick question if we have time.
Of course, yeah, I have time.
So I'm very interested in this idea about the targeted alias analysis. And I was wondering what your experience has been once you sort of look at a code base, figure out there are lots of false positives, come up with like the typical patterns that are causing this, and then you create the targeted alias analysis. What's the kind of effort and expertise needed? Again, this is probably a subjective question, but I was kind of curious, you know, does each new use case require a lot of additional thinking? Does it require PL experts, or this is something that typically developers can be taught?
Good question. This is not something that I would expect most developers to be able to do. So our experience is kind of preliminary here, but it takes a good amount of expertise to be able to study code and figure out a good way to do an analysis to catch the cases that we're looking at and reduce false positives. This is like PhD level expertise per now. I could imagine in the future, maybe having some templates that would make it easier for an end user to sort of enable certain types of analyses on their code base. But that's well beyond where we are right now. So I'd say this is still kind of new, this whole paradigm that we're studying. And I don't think we've done enough work to be able to generalize yet about, will there be, new patterns in every program that we can handle? We just haven't studied that yet. For now, we're looking for very general patterns that, pretty obviously apply across all the programs that we've been looking at.
Thank you.
Thanks.
Okay, thank you very much, Manu. So any more questions?
Yeah, and of course, feel free to reach out to me after the talk. And I've posted the links on this slide, so go check out the tools and try them out, and we're very happy to get feedback.
Okay, yeah, I think the end of this session. So let us join me to thank Manu for his excellent talk. And any questions, just feel free to reach him. So that's pretty much, we are closing our workshop. So we are very lucky that we have quite a few excellent speakers, and hopefully going to join again next year. Hajun, anything you want to say?
Nothing particular to add. I think it was a great workshop, and thanks to every speaker, in particular Manu. Let's see next year offline, I hope.
Sounds good.
Okay, yeah. Thanks, Manu. And we're gonna to if later on we can check the video, and then we can put on the YouTube to make it more accessible to other audience which may not be able to attend today. And thank you very much.
Okay, that sounds great. Thank you so much for inviting me. This was really fun.
Okay, yeah. Thank you. See you.
Okay.
Thank you very much. Bye.
Bye-bye.
Haju, I guess we're gonna have to go to bed.
Oh.
Yeah. So later on, I think I'm going to ask one of my students to check the video, and I believe stop recording now. So I think then I try to just put all the videos online and put them somewhere else rather than release. Then we can let the speakers check whether they want to release their videos and put on the YouTube. What do you think?
Yeah, great.
Yeah. Okay.
So we have to get permission from the speakers, right?
Yes, we need. Yes. So we probably just provide them a private link, and then they can first check whether they think the video is okay for them, and then we can release that. But I think for the I think for the first talk, I believe I need to ask the speaker, because the first I think first 1 or 2 minutes, I think we didn't do the recording. So I'd rather ask them whether they would like to just do a makeup, like put the first few slides and do a recording and send to us. We can put them together. So yeah, I think other than this, I think everything goes well. It looks to be a very good workshop this year. Also, thanks for your efforts. Yeah,
I think so. It was great
Yeah.
than expected.
Okay.
So
Anything else you want to add?
No. What time is it there? 5 a.m.?
5, yes. So already in the morning, I think. Yeah.
Take a sleep.
I have to take sleep, and then yeah, you don't have class tomorrow, right? Do you have any class?
No.
Okay, that's good. Okay, so yeah.
Okay, so
catch up
let's
with
keep.
you later, so we can, after I finalize the video, then we can have a look.
Okay.
Okay, yeah, bye.
Okay, see you. Bye.
See you.